want to just show you two things as we wrap up this section. The first is that it is possible to have a function of more than 3 variables. Generally, if we do that, rather than saying, okay, we've got x, y, z, w, now do we just keep going backwards? Generally, what we would do is just say x1, x2, x3, x4. This would be like a function of 4 variables. Rather than going through different letters of the alphabet, I'm just going to use subscripts. And I could say something like this is, oh, x1 squared plus x2 squared plus x3 squared plus x4 squared. And the graph of that then would consist of points in 5 space, because I would have a 4-dimensional input plus my output, which of course is just a number. Okay. I'm not going to try to visualize what that looks like, but I can work with these functions algebraically. All right. The other thing I want to show you is that there are some questions in the homework that are asking you to graph various functions. Basically, you're figuring out what graphing techniques we've already covered apply to that particular function, rather than having things given to you as a cylindrical surface or a quadric surface or something like that. You might need to manipulate the formula to see that that's what you're getting, or that you're maybe getting part of a quadric surface, something like that. I do want to just show you one trick with planes, because up until now, we've pretty much represented our planes as parallelograms. And that's the standard way to represent a plane if it's parallel to one of the coordinate planes, or if you're getting it as the extrusion of a line. But if I have something like this, f of xy equals 4 minus x minus 2y, something like that. Okay. Remembering that this is just a name for z, I could rewrite this as, let's see, if I moved over the x and the y, x plus 2y plus z is equal to 4. Okay. Now, I'm going to be a little bit hard-pressed to figure out what parallelogram I would want to draw to represent that, because this isn't going to be parallel to one of the coordinate planes, and I'm not simply getting it as the extrusion of a line from one of those coordinate planes. What I can do instead is represent a plane with a triangular section of a plane. Here's what I'm going to do. I'm going to just draw in this case, I've just drawn in the positive x, y, and z axis. I can sort of see that I'm going to intersect those axes at positive numbers. If I were intersecting at negative numbers, I'd draw in the negative axis. But I can now figure out, where do we cross the x-axis? If we're on the x-axis, both y and z would be 0, so we would have x equals 4. So I would have this point here, 4, 0, 0. Where do I cross the y-axis? Well, I would cross the y-axis when x and z are 0. So that would give me 2y equals 4. Y would have to equal 2. So that would be this point, 0, 2, 0. And then, where would we intersect the z-axis? Well, that would mean that both x and y were 0. So we just have z equals 4. So that gives me this point, 0, 0, 4. 3 points we've seen are enough to determine a plane, and if I just connect those, what I'm getting is this triangular cross-section of a plane. So if you're given an equation like this, where it's not parallel to one of the coordinate axes, and it's not the extrusion of a line parallel to one of those coordinate axes, it's perfectly acceptable to represent a plane by simply plotting the 3 places where it crosses the axes, and then connecting them to give you a triangular section of the plane. Of course, the plane continues infinitely far in all directions, but this sort of gives me a sense of where it is, and I happen to be, and since I had positive intercepts here, we end up drawing the portion of the plane that lies in octant 1, but that's enough for me to visualize the rest of the plane.